Hello, and welcome everyone to a special physics segment in today's news. We'll be talking about a specific experiment regarding constant acceleration. Now, in this experiment, we simulated constant acceleration by using a glider on an air track and using a weight to push it along the track with gravity to capturing the results in a position versus time graph. Our objective in this was to first get a theoretical acceleration, getting the weight of the thing and comparing it to the real acceleration we will later get and trying to get it within a 10% margin of error. How we get this real acceleration is using the Pascal capstone software, which just allows us to visualize the acceleration line and actually make the position versus time graph we talked about. To do this, we need a few materials, and for those, before we get to the materials, we need to talk about the relevance. Why knowing constant acceleration is important? Well, constant acceleration is something we see daily because of gravity. Gravity is 9.81 meters per second, and it behaves pretty consistent, which is why it's called a constant. Uh, and if we know how to handle this constant acceleration, it can help us to calculate trajectory for rockets or going down inclines, which can help us make stuff easier. Now, the materials we need is a pulley and the weight I was talking about earlier. This will make it so we can pull the glider along, and that way we don't really have to use any strength results. A scale, so we can measure the weight we're using on the weight. The glider itself, so we can move it along, and this is the important thing. It's what makes us be able to graph, well, not graph, but like the thing is moving around. An air track, this gets air pumped into it and makes the glider be able to move smoothly because it has no friction because of the air. The air pump to pump air into the air track. Motion sensor, this captures the movement of the glider along the air track and then sends it to the computer and the Pascal software where it is graphed, and we can then add extra points to it and show the velocity and the acceleration graphs as well. Now, I'll be moving along to the procedure. There's some videos I have here for you to see where it's actually moving along and the different graphs. We'll be back later with the data analysis. Ready? 3, 2, 1, go. I think I read my hand there. No, I think I read my hand. Ready? 3, 2, 1, go.
That's where the problem was. We had it too close in. I had to get out a little more, just keep going more.
Ready? 3, 2, 1, go. How's that one?
That was good. I think we should start it a little bit.
Really dark. And then we're saying.
You get my same color. I made my hair more curly.
I got it.
Get the full graph. Like, yeah, like that. Yeah. Like this, no? There you go.
Okay, and then we pick.
Oh, I'm sorry.
Do we need to make any marks on it or no?
Yeah.
Oh yeah, we need to. And then after that, we're just missing the math.
Somewhere about here, I think. When it's going down, right?
What?
When
yeah,
it's going down.
I think so.
I think we gotta pick one closer. And then how do I zoom it in?
What do you mean?
Like, like that way. I don't know.
It's just like that. No?
Okay, that's good. I guess.
Oh, no,
Yeah.
no.
Okay. So these are the numbers.
Amazing. Good. Awesome. You guys are killing it.
Is this the first bounce?
Yes.
First bounce.
I mean, nothing else is before. No, well, this is the first bounce. This is like the first going towards the.
That's the descent. That's the where it hits the bottom of it. It bounces up and hits it again.
It's going bump, going bump, going bump. If you were unable to tell what was happening in the videos, don't worry, I'm here to give you a brief explanation. In the first video, it was just showing us setting up the air glider in a way that it would bounce. We did a few different tries, some were farther away, some were closer, but we ended up finding a pretty good spot where it would bounce consistently and wouldn't fall off. And in the second video, it was just more of the graphical side, showing how we were setting up the velocity and acceleration graphs within the other graph, the original graph, as well as selecting the points we would use for the data and sharing between ourselves what we thought was happening. Now we can continue. We were able to properly graph and get the necessary data points to complete the equations given to us and compare our theoretical acceleration to our actual acceleration. Unfortunately, we were not able to get our acceleration to be within a 10% margin of error. We considered many things, such as maybe one of us was pushing it, or maybe it was just something to do with the weights. But in the end, we were unable to figure it out, and we stuck with the one we thought was best. In which case, it was a 20% margin of error. Still, we were able to get all the necessary data and get pretty close to it. So I would call it a success. Hello and welcome back everyone. We're here with the data analysis. First off, before we show the graph, I want to move to the theoretical. As here as you can see, we got the glider mass and the hanging mass. We got these by using the scale I showed earlier in the materials. And then after that, we simply divide the hanging mass by the glider and then multiply it by gravity. Gravity being negative due to it being pulling down. And if it were to pull up, it would be positive. So in this case, we got our theoretical acceleration of negative 0.91. Now, going to the data itself, as you can see here, this is how it looks. The top one being position versus time, then velocity versus time, then acceleration versus time. The position versus time one, as you can see, is kind of bumpy because, as you saw in the video, it was going kind of back and forth because it was bouncing on the string at the end. Velocity is a bit more like waves because it was slowed down as it got closer and then got a bit of speed. And acceleration is more jagged as it was more of like because this is constant acceleration. Velocity 1, velocity 2, we got here. We can see here the calculations done. For velocity 1, we got negative 0.1. For velocity 2, we got negative 0.4. We then use these for our first acceleration. And that's how we get our negative 1. For our second acceleration here, we use different points, and that's how we get our negative 0.76. For the third acceleration, we go back to the graph here. The graph itself took the mean for us, so without having to get any specific points, we are able to get the mean of negative 0.77. Now, unfortunately, this isn't within the 10% that we wanted, the 10% margin we wanted, and it's only a little higher than that. But we are moving to the conclusion. In conclusion,